Okay guys, so previously we have discussed the compatibility condition. Okay, now we will discuss the rigid body displacement condition. Okay, means as we have discussed that the selected displacement model should satisfy the rigid body displacement condition. So what do we mean by this rigid body displacement condition? Okay, so displacement model should include the rigid body displacement term in your polynomial shape function. It means that in displacement model there should be a term which permits all the points on the element to experience the same displacement. Okay, so there should be one term, so it will permit all the points in the elements to experience same displacement. So it is obvious that if such term do not exist, which will shift the origin of the coordinate system and which will cause the additional stresses and strains. Okay, so if such terms which will if it is not included the rigid body displacement term in your polynomial shape function, then it will shift the origin of the coordinate system and which will cause the additional stresses and strains in the element. Okay, so as we know that for example, if we consider a linear two-dimensional polynomial shape function such as a1 plus a2x plus a3y. Okay, so a1 term, it will provide for the rigid body displacement. Hence, to satisfy the requirement of the rigid body displacement, there should be one constant term in the selected polynomial shape function. So this is about your rigid body displacement requirement. Okay, so if we need to satisfy this rigid body displacement term or rigid body displacement condition, we need to select the polynomial shape function in such a way that it should consist one constant term in two-dimensional polynomial shape function. Then and then only the rigid body displacement condition will be satisfied. Okay, now next third condition is what? Your third requirement is what? The constant strain rate requirement. So similarly, constant strain rate requirement, for this constant strain rate requirement we need to have some term which is related to your constant strain rate. Okay, so the displacement model, it must include the constant strain rate of the element. This means that there should exist combination of values of the polynomial terms. Okay, so it means what? There should be some values of the polynomial shape functions which will cause all the points in the element to experience the same strain. Okay, as we have discussed in for rigid body displacement, for this case there should be one term which will permit all the points on the elements to experience same displacement. Similar way, for constant strain rate condition, there should be some terms or combination of some values of the polynomial shape functions which will cause all the points in the element to experience the same strain. In previous case, same displacement. Now in this case, such terms should be there which will cause same strain rate. Okay, same strain in each element. Okay, so and the necessity of this requirement, which is understood by physically. What do we mean by this? If we imagine the refinement of the mesh as these elements approaches infinitesimal in size, it means what? All the infinitesimal sized elements should have constant strain value. Then and then only we can say that the constant strain rate condition is satisfied by this selected displacement function. Okay, so as we know that, now how we are going to satisfy this constant strain rate condition here. So let us consider a two-dimensional polynomial shape function. Okay, a quadratic two-dimensional polynomial shape function in which the terms are like that. This displacement function u is equal to what? a1 plus a2x plus a3y plus a4x square and so on. Okay, so first three terms are like that, a1 plus a2x plus a3y. Now this a2x and a3y, these two terms will provided for uniform strain in x as well as in y direction. So a2x and a3x, these two terms are provided for uniform strain in x and in y direction. So if we need to satisfy the constant strain rate condition, we need to have some terms which will satisfy the constant strain rate in the element. It means what? Which will cause all points in the elements will and which will experience the same strain. Okay, so we need some terms in our polynomial shape function. So this is about your constant strain rate condition. So for rigid body condition or rigid body displacement, we need to have some terms which will cause same displacement, but for constant strain rate we need some terms which will cause same strain in the element. Okay, now next one is what? Your geometric isotropy. Okay, so this geometric isotropy, it is nothing but if the terms used in the polynomial displacement functions are symmetric about the axis of symmetry of the Pascal's triangle. As we know that Pascal's triangle is nothing but a symmetric triangle, okay, about its axis of symmetry. So if the terms used in the polynomial displacement functions are symmetric about axis of symmetry of Pascal's triangle, then it is called as the geometric isotropy. Okay, or there are 2 to 3 some guidelines to construct the geometric to construct the polynomial series with desired geometric isotropy. Okay, so what are these two guidelines? So polynomial of order n that are complete have geometric isotropy. So the polynomial, if we consider a linear polynomial shape function, so for linear polynomial shape function, when we call it as a complete polynomial shape function, so for completeness of this polynomial shape function we need to have 3 terms. Okay, 3 terms means constant plus x plus y. Okay, so these 3 terms should be there to have this complete shape function. If we consider a quadratic shape function, as we have discussed this in your Pascal's triangle, if we consider a quadratic shape function, then for completeness of this quadratic polynomial shape function we need to have 6 terms. First one is your constant, 3 then x, y, then x square, x, y and y square. So these 6 terms should be there to complete the to satisfy the completeness requirement of the polynomial shape function. So if the selected polynomial or selected displacement function is complete in nature, then we can say that geometric isotropy is already satisfied. Then second guideline is what? The polynomial of order n that are not complete. Okay, suppose let us say if this polynomial is not complete, but yet there are some appropriate terms which will satisfy the symmetry of that polynomial shape function, then we can say that the geometric isotropy is satisfied that selected displacement function. Okay, so in this way you can check or you can satisfy the geometric isotropy for that selected displacement function. Okay, and last one is your C0 and C1 type of continuity. So as we have discussed this C0 and C1 in your previous lecture, so as we know that for C0 we need to satisfy the displacement requirement. Then for C1 type of continuity we need to satisfy displacement as well as slope requirement. As we know that for truss problems there is only displacements in x and in y direction, but for beams or for plates or shell problems there may be some slopes will be occurring in the elements. Okay, so there should be this displacement model should satisfy the displacement as well as your slope requirement. Okay, so such type of problems are classified as your C1 type of continuity, and if only displacement is the requirement, then such type of problems are classified as your C0 continuity. Okay, so this is about your convergence requirement or convergence criteria for the displacement model selected. Okay, so displacement model selected displacement model or selected displacement function should satisfy these 4 requirements. First one is what? It should be compatible in nature. So compatible in nature, it means it should satisfy the C0 as well as C1 continuity. It means it should satisfy the displacement as well as your slope continuity. It means the selected displacement function should be continuous. Okay, next one is what? Your rigid body displacement. So it should have some terms which will satisfy the rigid body displacement. As we know that the constant term will satisfy the rigid body displacement. Then next one is what? Constant strain rate. So constant strain rate means what? There should be some terms which will satisfy the constant strain in the elements. And last one is your geometric isotropy. So for geometric isotropy, as we know that for geometric isotropy, the selected displacement function or selected polynomial shape function, it should be symmetric about the Pascal's triangle's symmetry axis. Okay, so in this way you can get the exact solution by using these 4 criteria. Okay, so this is about your convergence criteria or convergence requirement for the selected displacement function. Okay, so up to this clear. Now in next lecture we will see the constant strain triangular elements, then rectangular strain triangular elements. Okay, so here I will conclude this lecture. Thank you.